Last time we discussed design against static load, right? So today we'll start with
हाँ सर.
design against fluctuating load, right? So before starting this, you are having a session on Friday, right? Usually at 7 to 8. Hello.
Yes sir.
So that is shifted to Thursday for this week. Okay.
Okay sir.
Okay. Okay. So now let us start with
With
this.
the ma'am's class.
Yes. Yes. Yes.
Okay.
Okay. Okay. So let us start with this design against fluctuating load. So last time we have seen this design against static load. So as we have defined the static load as a load which is not going to have change in direction or magnitude with respect to time, right? Here this fluctuating load, as the name suggests, it is going to have variation in its magnitude as well as direction as time goes on, right? So before discussing that fluctuating load, some of the terms we need to consider, right? So the one of this is this stress concentration, right? So as you can see in this given figure, we are having a hole in a particular plate, right? So whenever this kind of discontinuity or irregularity is there in the cross section, the stress at the discontinuity is higher than the stress calculated by the elementary equations. Now what are the elementary equations? Elementary equations is which we have discussed last time, like that sigma naught is equal to P by A for axial stress. Similarly, for bending stress, we have discussed that mdy upon I, and similarly for the shear stress, that is the torque into this radius divided by polar moment of inertia. So these are all elementary equations, right? So whatever stress you are going to calculate with this elementary equation is not the same acting on the component while it is in service when there are any this kind of discontinuity or something is there. So for that you can measure it with some specific technique, right? So that technique is known as this photoelasticity technique, right? Photoelasticity technique. So in this photoelasticity technique, basically you are having a particular component which is made up of epoxy resin, right? And that component is going to undergo certain experiment with some standard dimensions and all under that circular polariscope, right? So it is going to measure the actual stress experienced during the whatever force we are going to apply, and because of that stress is going to generate it, right? So as you can see in this given figure, the localization of stress is there wherever this kind of discontinuity is there, right? So this is how we need to consider this stress concentration in whenever we are designing this kind of component which is having irregularity, right? Because in practice we cannot have what we can say same cross section throughout, because in case of if we discuss about the shaft, then on shaft we need to mount gear, so you need to provide some keyways, so the keyways is the discontinuity. Similarly, some particular gears are having that oil grooves through which it needs to be oiled, and so this kind of discontinuities will always be present in your machine components, and wherever this kind of discontinuities is there, there will be stress concentration. So this particular what we can say experimental calculation of this kind of stress is calculated, right, by an what we can say scientist, right? And they have produced this kind of graph which is here presented in this figure 5.2. As you can see, this particular figure shows the stress concentration factor, right, against the d by w ratio of this particular component which is mentioned here. So again here you can see this is a plate with hole, right? So in this they have plotted this stress concentration factor as the d by w ratio changes. So what is this stress concentration factor? So actually this stress concentration factor is that maximum stress which is actually acting to the that nominal stress which you are calculating with this elementary equations which we have already discussed, right? So always this stress acting is higher than that calculated with those elementary equations. So that is why this stress concentration factor has come into picture, right? This is here for normal stress. Similarly you can write it for shear stress also. This Kt may be equal to this tau max upon the tau naught, right? So now why this 1 second, let me check somebody is there. So now why this kind of discontinuities are there? So there are various reasons for this discontinuities, right? Sometimes it may be variation of material properties, right? As we know that whenever that machine that component is prepared by some of the process like casting, it may happen that at all the place it is not homogeneous. Or 1 second. नहीं, 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 हाँ, so yes, here we were discussing about why this kind of this discontinuities are present, right? Or why this stress concentration takes place. So one of the reason may be variation of that material property, other may be the load application. So if we observe in some of the cases this load application is localized, like in gear drive, wherever that contact is there, at that point high stress concentration is there. Similarly in hooks also, very localized area is experiencing that force, so there is also chances of high stress at that particular point of contact, right? So apart from this, there may be some abrupt changes in cross section that we have already discussed, right? Like in case of those shafts and all, we need to provide that keyholes and some oil grooves and all. So that is abrupt changes in this cross sections, right? Similarly there may be some scratches present on the surface, so those scratches present also may lead to stress concentration, right? And this graphs are first prepared by that R.E. Peterson, right? This particular figure 5.2 which you are seeing, in that this particular component is taken, and for this component various ratio of this D by W, which is mentioned here, what is D and what is W. D is the diameter of hole and this W is the width of plate. So by changing this D by W ratio, that the stress concentration factor is plotted, right? These are all based on the experimental data, right? So similarly it is made for some other geometry also. I guess it is mentioned here here only, I guess, in this slide, not there. We will see, I guess, while discussing example, we will see here it is for this kind of plate, so it is also discussed for this kind of shoulder, right? Like wherever we are having that change in cross section,
So what's
right?
sigma
So
zero?
sorry,
Sigma zero.
sigma 0.
What is sigma zero? Sigma max is the limiting value.
Sigma max is the maximum force which is measured, right, with some experimental technique or so. And this sigma 0 is calculated with this elementary equation as we have discussed, right? Hello.
Okay, sir.
Sigma zero is there, no sir. The level of stress in that case is very low, or it is zero only.
See, sigma naught is the theoretical stress which we are calculating with this kind of elementary equations, right? So suppose if you want to calculate a stress generated in this particular cross section, then you will consider your area as that W minus D into whatever thickness of your plate. Yes or no? Hello.
Yes, sir.
Right. So when you are going to consider this and calculate that sigma naught, you will have certain stress generated. Yes.
Yes, sir.
So this stress generated is actually less than whatever experienced in practice, right? Or whenever experimental measurements is there, then it is having higher value. So that is why that is sigma max, which is experienced by the component. Are you getting now?
So we can define that sigma naught.
Yeah, that sigma naught is that nominal stress obtained by elementary equation, right, for minimum cross section. Okay.
Okay, sir. Thank you, sir.
Okay. Okay. So now, one second. So again, you can see my screen. Hello.
Yes, yes, sir. Visible, sir.
Okay.
Yes, sir, it's visible.
Okay. So now let us go to the next one. So in the stress concentration, as you can see here, if we are having this kind of some elliptical hole, then this theoretical stress concentration can be given by this relation 1 plus 2 into A by B, where A and B is mentioned, right? This half width along this vertical and this along this horizontal, or we can say along the application of this force and perpendicular to the application of force, right? So this is how you are defining this kt. So if you see in this figure, if your b is equal to 0, then this kt will almost tends to infinity, because it is a crack, and whenever the crack is there, then stress concentration will be very high, right? So when that b is equal to 0, you will have this kt almost infinity. Similarly, if it is a circle in place of this ellipse, then what is going to happen? A will be equal to b. So in that case, kt can be calculated as 1 plus 2, that is 3, right? So this is how you are having this stress concentration. And here, to understand this stress concentration, this that fluid flow analogy is taken, right? So as if we assume that fluid is passing through a channel, then it will have this kind of flow lines, right? Similarly, stress is also flowing, we are considering, right? And whenever that cross section is going to reduce, there will be definitely increase in the stress. So that is known as stress concentration. And as you can see here, these sharp corners are having more stress concentration in comparison to this rounded corner, right? So this is how you are having stress concentration, right? So now we can reduce the stress concentration by applying certain methods, right, for different kind of geometries. So here the reduction of stress concentration due to V notch is presented, right? So here in this figure A, original notch is given, right? So if this kind of notch is there, then you will have this kind of stress concentration. It means this very high stress concentration will be there, right, in this particular case. Now if you want to reduce this this kind of highly dense stress line, then you can provide this kind of multiple notches, right? So from here only you will have some kind of uniform distribution or something like that, right? So there is one way of reducing this stress concentration. Other way is to provide this kind of drilled hole, right? And that is mentioned in this figure C. And finally, if you are going to remove that portion itself, right? So removal of undesirable material, that is given in this D. So this way, there are various ways which will help you in reducing the stress concentration. In case of reduction in stress concentration in shaft, right, with keyways, as we have discussed, on shaft you need to provide this keyways, because it is going to help you in mounting gears, right? You know that shaft is carrying key which is attaching the gears which are mounted on it, right? So this keyway is going to increase the stress concentration. Now if you are going to this is original shaft in A, figure A, original shaft with this keyway is there, right? So what we can do to reduce this is we can provide this relief or radius at this kind of sharp corners, right? As you can see, right, we can provide that radius at this sharp corners to reduce the stress concentration. Apart from that, we can drill this hole, as you can see here, it is mentioned in this figure B. So this is going to help you in reducing the stress concentration, right, in that shaft.
Sir, I have one doubt.
Yes.
Sir, by providing more notches and by padding drill, how stress concentration decrease?
Actually, in that case, as we have seen, this particular stress line will be trying to be uniformly distributed in this area, while priorly what happened if you are having only this kind of that discontinuity, that stress line is coming till here, all the stress line is coming like this, right? And it certainly at this point it will try and go this way, so there will be a more dense stress line will be there, right? Now instead of this,
Yes,
if you are having this kind of various already notches are present, right, like this, so in that case what will happen, this stress line will start deviating from this only, and it will have certain kind of this uniform distribution in comparison to this earlier one. Are you getting? Hello?
yes, sir. Yes, sir. But
Yeah.
sir, one question: by providing more notches, material may be weak.
uh, that may happen, but see, what our main aim is to reduce the that maximum stress generated, right? So if maximum stress generated can be reduced by providing this hole, then material is not going to undergo yielding or fracture or something like that. Are you getting?
Yes, yes,
Right, so it may happen that stress may go up in this region also by providing this kind of hole, but that whatever the rise in stress is there is still less than that yield stress or ultimate stress, so that our material is not going to fail. Are you getting what I am trying to say?
yes, sir.
Right, in this particular case it may happen that sigma max is going to what we can say surpass the value of sigma of y or sigma of ut, right, in this first case in figure A, right? But in case of B, C or D, this sigma max is not going to surpass the sigma of y or sigma ultimate, right? It may happen that in this whole region overall value of stress may rise, right? Previously it may happen that here in this region value of stress may be 70. So while providing this kind of solution, it may happen that in this region also it may go to 90, right? But in this particular case it may happen that here the stress is reaching to around 120, right? While in this case it will still remain around 100. Are you getting what I am trying to say?
Yes,
So this way you can reduce this stress concentration. Okay.
yes, sir. Get it.
So after that, in this kind of abrupt change in cross section, that is also result in this stress concentration. So here also they are providing this fillet radius, and they are providing this kind of undercut and notches, right, to reduce the stress concentration. After that, we are having this reduction of stress concentration in this threaded components. So in threaded components also you can see there is a continuous change in this cross section, so it will result in stress concentration. So in order to avoid this, you can again provide undercut, or you can reduce the shank diameter as it is mentioned here. Here it is the shank diameter is higher, right, in comparison to this one. So by this kind of solutions you can have reduction in stress concentration, right? So once you are done with this, here this is that figure, this 5.3, which is showing this shoulder, right, in plate as we have discussed. So here again you can see this kind of theoretical, this stress concentration factor KT is plotted for different geometries. Right now, here you are having a numerical, right? So actually this numerical is based on this stress concentration and all, right? So a flat plate subjected to tensile force of 5 kilonewton is shown in this figure. Now the plate material is grey cast iron, right, Fg200, and the factor of safety is 2.5. Determine the thickness of the plate. So here actually what you can see in this problem, can anyone say how we can start approaching this problem? Hello.
Yes, sir. Just
Yes. So can anyone say?
So again, question.
Sorry. Yeah. So can anyone say how can we proceed? So based on
Sir,
our
at the drilled hole, sir, at the drilled hole, we will find out the nominal stress, and by the value of the stress concentration factor, the actual stress can be formulated.
okay, that is one thing.
Then
Okay,
it fitting.
anyone else? Hello, anyone else? See, you will consider stress concentration at hole, right? And at any other place are you going to consider the stress concentration?
सर मतलब जहाँ पे डायमेंशन चेंज हो रहा है, द डायमीटर चेंज हो रहा है वहाँ पर, सर वो जो पीछे ग्राफ था जस्ट पिछली स्लाइड में उसका यूज कर.
Here only this shoulder graph is there, right? That what we can say, this plate with varying cross section, right? As you can see, it is mentioned here. Plate with shoulder fillet is given, right? So this also
Yes.
will give you increased stress. So you need to consider stress concentration at two places.
sir.
First is because of hole, right?
Sig.
Yeah.
Hmm.
And second is because
So,
of the shoulder in the plate. Yeah. Yes, please. Hello.
no, sir. No, sir. Nothing. Actually, I was telling that should we first calculate the sigma max, then after that, the whole section of the fillet
Yeah.
we
First
have to calculate.
you need to calculate sigma max. How you will calculate sigma max?
Uh,
For
as
that you must have that
okay, sir.
ultimate stress, right? For grey cast iron, that is 200
Ultimate stress. Yeah,
Newton per
it's
mm.
200 and
Factor of safety is given as 2.5. So from
2.5. Then
how can
that
you
would be
calculate
divided,
sigma
which
max?
would be a
As you
sigma
can
max is
try.
equal to the ultimate tensile test and by factor of safety, which is 80.
Right, you will get like this, yes or no?
Yes, sir. Yes, sir.
Okay, so once you get this, then you are having two discontinuities. One is at hole and other is at shoulder. So if you consider for hole, then for hole this sigma naught is given by P by W minus D into T. So if you consider this P is 5000, right? 5 kilonewton. W minus D, W is what? Width, that is 30, right? and d is diameter, that is 15.
Diameter. Yeah.
So 13 minus 15 into t. So and in this sigma naught will be then 5000 by 15, right? 5000 by 15t. But here for sigma max in this region, when we are considering this hole as discontinuity, kt into sigma naught. So now for hole kt, how will you come up with kt in case of this discontinuity at hole? So for that you are
Sir,
having
1 plus 2. 1 plus 2, 3 kt.
so it is not simple plate, I guess. So what you should do is you should check here in that graph, I guess. One second, let me show you that graph. Can you see this graph? In this
Yes.
graph you need to check that d by w. D by w. What is d by w in our case? 0.5? Yes or no?
Ha sir. 0.5 or
So 0.5
2.
is going here somewhere. 2.15, 2.16. Can you see?
2.
1/6 you can take, or 2.15, 2.16. So for
Sir,
now
if we take 2.15, then what problem would it be?
there will not be that much problem, but whatever you take, see here this graph are not that clear, right? But
Huh.
in practice it is
But sir,
even more
as
clear.
it is in between of 2.1 and 2.2, so therefore.
So for now you can take 2.16, right, that kt. So 2.16 into 5000 by 15t. So can you calculate and tell me what is this? We are considering this discontinuity, right, for now.
Okay, sir.
So what is this? If you simplify it, what are you getting? Hello?
Yes, sir. Yes, sir. Just doing, sir.
So if you consider this
9.
actually 2.16, if you take, then it will be 0.72 by 5. 5 into 3, 15, and 0.7 into 3 will be 2.16. Now into 5000
720
t. So it will
720
be
by t.
720 by t. Right. Now you need to calculate for shoulder. So for shoulder, what will be your sigma naught? It will be p by dt, right? D is what? 30. So 5000 by 30t will be your sigma naught, and sigma max will be that kt into the sigma naught. So kt in this case is, how will you
2.16.
kt here will be from figure 5.3, right, this one. So from this figure, if you check this capital D by small d, what is capital D by small d in our case? Check the figure. Yeah, capital D by small d is what? This is capital D, this is small d. So capital D by small d is equal to 55 by 30. That is 1.5.
1.5.
And this small r by d, what is small r by this t?
Which is 0.167 would it be?
Okay, that is 5 by 30, right?
0.167.
1.67.
0.167. So if you have both of this, then you can now see that graph. Let us see that graph. 1.5, which is this one, this line, right? 1.5 means this line, and then R by D is 0.167. So here it is 0.12141618, and then so 0.16 will be here, 0.18 will be here, so 0.167 will be somewhere here, I guess. So 1.8 you can take, right? This will be there, right? Let me draw vertical line from there, right? So this way, I guess from here. But 1 second. This way. Okay. So this way it will be KT is equal to 1.8 from this figure. Right. So if you take this KT is equal to 1.8, then here what will happen? 1.8 into 5000 by 32. So what it means, please mute yourself. So what are you getting in this?
300 by T.
300 by T. So which stress is maximum among these two?
Whole wala, sir.
That is 720 by T.
720 by.
So that 720 by T is maximum. So it will be then compared to that particular stress
Permissible stress.
which we have calculated. So T will be 9 mm. Okay. Is it clear?
Yes.
Okay. Now let us go to the next thing. That is fluctuating stress. Now fluctuating stress means you are having that variation in stress, as we have discussed, right? So there are various types of fluctuating stress. Here that this types of cyclic stress is mentioned, right? So in this it is classified as fluctuating stress, repeated stress, and reverse stress. Now fluctuating stress, in that case your stress will be having a mean stress about which your maximum and minimum stress will be there, right? As you can see here, you are having some maximum and some minimum stress around a particular mean stress, right? It may be both tensile, both compressive, or a combination of this tensile and compressive in case of fluctuating stress, right? So this is how you can have fluctuating stresses. So once you have that fluctuating stresses understood, then you can see repeated stresses. So in case of repeated stresses, again you will have that fluctuation about this mean stress, right? This is sigma m. But here in case of repeated stress, minimum stress will be always 0, right? So this is how you will have this repeated stresses. So it will go to a maximum and again come to 0, and again that cycle will be repeated, right? So, and finally in case of reversed stress, your sigma mean will be equal to 0, and about that you will have maximum and minimum stress. So this is how various nature of stress is there, right, in case of this different cyclic stresses. So here in each figure you are looking this sigma m and sigma a is mentioned, right? As you can see, sigma m, sigma a. So basically what are this sigma m and sigma a? So sigma m is mean stress, which can be calculated with this 1/2 sigma max plus sigma minimum. Similarly, this sigma a is stress amplitude, which can be measured with this sigma max minus sigma mean. right? So this is mean stress, this is stress amplitude. Right, so this is how you are having these various types of cyclic stress. As you can see, in case of repeated stresses, your minimum stress is always 0, right? So your sigma m and sigma a are same because minimum is always 0. So sigma m and sigma a both are sigma max by 2. Now if you go for this reversed stress, so in that case your sigma m is equal to 0, right? So in that case your sigma a will be equal to your maximum stress, right? Because it is having the same value on both the sides, right? So here sigma max and sigma mean is having the same value, right? So this is how you are having these various types of cyclic stresses, right? Once you have idea about this kind of fluctuating stresses, then we can go to the next concept, that is fatigue failure. See, fatigue failure is because of that repetitive load, right? As we have seen in the previous case, what happens whenever any component is going to undergo cyclic stress, then that component will undergo failure below the yield point, right? Or ultimate, below yield or ultimate strength, your component will undergo failure if it is having this kind of cyclic stresses acting on it, right? So that is known as fatigue failure, right? So this is how you can have your component failed before reaching to the yield point or ultimate point. So the simple example of this, I guess we all have experienced that simple experiment, right? As it is mentioned here, if we have taken that small wire, and then that wire may be made up of some metal, but if we try to means have if we try to have crack or fracture in that wire, then what we can do is we can apply cyclic stress, right? Continuous bending and unbending. So what is going to happen with continuous bending and unbending? As you can see, when this kind of force is applied on the wire, above layer will have tension and below layer will have compression. Now if you go to the reverse side, as it is mentioned in this figure, so what will happen? Reverse of what has happened earlier. So on that particular fiber, now compressive stress are there, and on this side of this particular layers are having this tensile stress. So as you can see, this is having that continuous change in the state of stress, and it is having what we can say this a reversal of load, right? Or nature of stress is changing, and it is having this kind of cyclic nature. So because of this kind of nature, it's this failure will occur prior to its yield strength or that ultimate strength, right? So this bending and unbending of wire can make fracture without reaching to its that yield strength or ultimate strength, right? So this is how the simple example of fatigue failure is there. Then you are having this endurance limit. So what just now we have discussed is that if we apply this kind of cyclic stresses, then we will have failure prior to reaching that yield strength or the ultimate strength. But now how we are going to define that, at what particular point it will going to fail, or at which stress it is going to fail, at what particular amount of stress amplitude of the cyclic nature your component is going to undergo failure, that how we are going to define that. So for that we are having this endurance limit. So in order to have idea about the endurance limit, what is being generally done is a specimen for this fatigue test is made with some standard dimension, as you can see in this figure. This This is standard geometry, and the finish of the surface of this component is also very high, so their stress concentration is not there. Now once you prepare this kind of specimen, then it is going to undergo this rotation, continuous rotation with the help of electric motor. Basically that component will be loaded on this testing machine, right? As you can see, this is the specimen which we have seen in that figure. So that specimen is going to loaded on this rotating beam fatigue testing machine. So here it will continuously undergo this rotation. When this particular 1 second, hello, હું અહીંયા લેબમાં ક્લાસ લઉં છું ભલે 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 હા 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 જય ભગવાન. Hello, can you hear me?
Yes, sir.
Yeah. So what we were discussing is this specimen is going to loaded on this machine, and then this will undergo this rotation, and it is going to have this weight. So by increasing this weight, you can change the stress amplitude, and when you are going to have this full rotation of this particular component, it will experience this bending stress as mentioned here. And when this specimen is going to experience this bending stress, as you know, the nature of bending stress is it will have compression on one half and the tension on the other half. So this A1 point is going to experience zero stress when it is here, while when it will reach to A2, it will experience the highest tensile stress. Now again when it will reach to A3, it will experience that zero stress, and then again when it will reach to point A4, it will experience the highest compressive stress, right, stress. So as you can see, the same point or the same layer is going to experience that various nature of forces and in various magnitude. So it is cyclic stresses acting on this particular specimen, right? So now once you are going to load this component, and then when you are going to provide this kind of rotation to this, it will experience different stresses, right? So once you have that data, then you can plot it on this SN curve. This SN curve is the stress against the number of cycle. So this is for that simple steel component, it is measured. So basically this is log plot is there of number of cycles and this what we can say, that endurance limit. So basically endurance limit is the limit below which, that endurance limit is the limit below which a component can work for greater than 10 raised to 6 cycles, which is considered as infinite almost, right? So endurance limit is the limit, right, below which if that reverse load are below the endurance limit, then your component can work infinitely without undergoing failure, right? So that is known as endurance limit, right? Now every time it is not possible that forces are below endurance limit. Sometimes forces may go above endurance limit. So in that case, what is going to happen is, if suppose you are having your stress acting is at this particular point, right? So it will be that log 10 with whatever stress, fatigue stress, it is going to be considered. Now fatigue stress means it is going to undergo a finite life, it will have fatigue failure. But then if this kind of stress is acting, then if we would like to have idea that what are the number of cycles your component or specimen will undergo without first crack or without failure, right, without first fatigue break or without failure, then it can be calculated by plotting this particular uh, line parallel to this horizontal line, and then again taking this to this horizontal line by taking parallel to that vertical line. So here whatever number of cycles you will get, that will be your number of cycles without undergoing failure. Right, here this 6 is log 10 10 raised to 6, right, that is why it is mentioned here as log plot. So basically this graph you are seeing is from that 10 raised to 3 to 10 raised to 6 cycle it is mentioned, right. So we will see low cycle fatigue and high cycle fatigue also when we go further. So basically first you need to have idea about endurance limit and that what we can say fatigue life. These two terms are important. Endurance limit means it is the limit below which if the stresses are acting, then component can work for infinite number of cycles. Now fatigue life means your stress is acting above endurance limit, so it will have some finite life which can be calculated from this SN curve. So is this clear? Hello?
Yes, sir. But sir, here
Yes, sir, it's clear.
in that curve, why log is used?
So
It's
it is for our
can't.
easiness, right? Because if you are having that in terms of that
Okay.
10 raised to
No, sir.
6, right?
If
So it can
uh,
be directly mentioned as 6 in place of this 1 to 10 raised to 6. Are you getting?
uh, so that's I got it. But sir, except log, can't we take E series or like that?
Here, see, E series actually you are having cycles in terms of this million revolution and all. So how can you relate it with E raised to something or what? Are you getting?
Hmm.
Okay.
Okay. Sir.
Okay. So now let us go to the next one. So that is this low cycle and high cycle fatigue. So as we have just now seen that the graph plotted was in this region only, high cycle fatigue only what we have seen. This low cycle fatigue is very rarely used, because what happens is low cycle fatigue means component is going to fail less than 1000 cycle, right, or less than 1000 cyclic stress, right. So if this small life is there, then what you can do is you can provide a very higher factor of safety. Instead of considering it as fluctuating load, you can consider static and provide high factor of safety. So this is how this low cycle fatigue is generally not being considered while we are considering this fluctuating load, right. And this endurance limit is clear, right. So actually your basically graph will start with this ultimate strength. So from that ultimate strength it will going to start this decreasing because of nature of cyclic load, right. So this is how and these are all failure points. So if your this number of cycle, so what this failure point suggests is if your number of cycle is let us say 10 raised to 5 and stress is here this much, so your component is going to fail in that case. Are you getting, right. So basically at 5, suppose 10 raised to 5 cycle, your maximum load allowed is this much. Are you getting? This may be considered as allowed, this one. Are you getting what I am trying to say? Okay. Okay, so this is how you are having this low cycle and high cycle fatigue. Then again some important things like this notch sensitivity and all is there, right. So notch sensitivity is actually whenever you are considering this theoretical stress concentration factor, it is not always providing proper results. So in order to consider this what we can say this lack of providing proper value, you are defining one more term that is known as fatigue stress concentration factor, right? So as theoretical stress concentration factor is not providing, so you are defining one more term that is known as fatigue stress concentration factor. So fatigue stress concentration factor is considered as this KF, right? How we are going to calculate this fatigue stress concentration factor is the endurance limit of notched free specimen. This endurance limit of notch free specimen and the ratio of this particular specimen to the notched specimen. Endurance limit of notched specimen. So now this actually related to the actual material, and it also affected by that grain size. So whenever greater what you can say, there is a greater reduction in this stress concentration, when greater reduction in endurance limit when we are having that fine grained material, because fine grained material will have more stress concentration in comparison to coarse grained, because fine grained material will have more number of grain boundaries. All grain boundaries are related to this increase in stress concentration, and when increase in stress concentration is there, that endurance limit will go down. So this is how you are having this fatigue stress concentration factor, which is related to this grain size and all, right? And basically this notch sensitivity is a susceptibility of a material, right, to avoid this damaging effect of stress raising notches, right, in fatigue loading, right? So basically this notch sensitivity is defined as this increase of actual stress, right, over this nominal stress, right? Increase of actual stress over nominal stress, right, divided by increase of theoretical stress over nominal stress. Right, now this both can be calculated from this fatigue stress concentration factor and theoretical stress concentration factor respectively. So actual stress will be given by this Kf into sigma 0, right, or the nominal stress minus sigma naught, and again Kt sigma naught minus sigma naught, because it is this basically sigma max minus sigma naught for both the case. So for one case we are going to use this Kt, and for other we are going to use Kf, right? As we know, both Kt and Kf are that sigma max upon sigma naught, right? So this is how this Kt sigma 0 minus the sigma naught, and Kt sigma naught minus sigma naught, and Kf sigma naught minus sigma naught is there. So if you further simplify, it will be Kf minus 1 upon Kt minus 1. So from this you can write your this Kf is also represented by this Q into Kt minus 1 plus 1. Okay, so this is how you are having this fatigue stress concentration factor and notch sensitivity related to each other. This is fatigue stress concentration factor, this is notch sensitivity, right? Now endurance limit approx estimation, that is also another thing you have to have idea about. So what do you mean by this endurance limit approx estimation? So basically, whenever you are calculating this endurance limit, let us say it SE dash, whatever you are getting from that experiment, right? Now whatever value you are getting from the experiment needs to be what we can say modified, right? Why? Because there are various factors affecting to when it comes to actual application. See, in your particular experiment, what you are using is mirror finish. You are using, right? What you are using is mirror finish, right? Then what you are using is specific shape you are using, right? Then a specific size of component is there, right? Then you are having a certain that reliability factor, right? Reliability of that particular what we can say experiment, right? Now, and stress concentration also needs to be taken care. So if you consider all this factor, right, then whenever you are going to calculate your updated or what we can say corrected endurance limit, then you are going to consider all this factor Ka, Kb, Kc, Kd, and you are going to correct your calculated endurance limit from experiment. This is your calculated endurance limit, right, from your experiment, where what we have seen that experimental setup, right? Now this is corrected or updated endurance limit. Now what are all this factor? So this is surface finish factor. Ka is surface finish factor. So as you know, in that component mirror finish was there, and in actual practice every component is not having mirror finish, or in some application it is not even required, right? So that surface finish factor, then this size factor, right? Then this is Kc is reliability factor, and this Kd is actually modifying factor to account for stress concentration. So it is related to stress concentration, right? So this is how you are going to what we can say modify that whatever endurance limit you are calculating from or you are observing from your experiment, you have to modify it, right? Because in case of experiment you are providing that bending stress, in which if you consider that cross section, as you can see, whenever this kind of profile of stress is there like this, from here, let me draw it properly. In that bending stress, actually what you are having is, if you see that stress profile will be like this, right? This from here to here it is going tensile to compressive, sigma T to sigma C. So what happens in case of this shaft and all, this, if it is a, let us say, shaft, right, then this particular area is going to experience the more amount of stress, right, which is highlighted with this particular hatch line. It is going to experience more number of means more amount of stress, right? As you can see, at other places not that high stresses are generated. So based on this you have to check, right, how your this particular things are affecting to value of endurance limit when it is not so in other cases, right? And apart from this, what we can say, in uh, uh, in case of experiment you are using that bending stress, so when it comes to that axial stress, that is going to be further modified by this factor 0.8, whatever corrected value you are calculating, that also can be modified in case of that axial stress acting on the component. So this is how you will have what you can say corrected value of endurance limit, right, at various places in various cases. Okay, is it clear?
Sir,
Hello?
hello, sir.
Yes.
How this component endurance limit connected with or related with uh, size?
See how it is related to size, that is what I'm telling, right? See, in this particular case of your that specimen, you are having, it is acting in very small component, right, and small area, right? When this size is going to be increased, in that case it may happen that that equal distribution of stress is there, which is not here in case of this particular case. And sometimes even your component may not be circular. Here in this case your component is circular, so in some cases you need to first calculate the equivalent diameter, right, and then you can proceed to what you can say modify your endurance limit. Are you getting?
But
Because see, size, as and when size is going to increase, whatever amount of those discontinuities and voids and all those things are present may also increase with increase in size, right? Are you getting?
getting
Okay, so this is how these various factors are there, right? So once you have idea about this, then we can go for this infinite life problems and finite life problems, right? Infinite life problems means whenever you are going to draw this ascent curve from this 10 raised to 3 to this 10 raised to 6, it will lie, sorry, one second. So it will lie uh, below this, and the 6 will be shifted to this, right? So that is why you will have this infinite life. So whenever your this stress is less than this, it can go for this infinite life, and whenever it is higher than this, it may have certain finite life. So are you getting this first, the differentiation between finite life and infinite life?
Yes, sir.
So let us see one by one then, right? Let us first see this infinite life. So can you try this one, in which it is mentioned that a plate made of steel with this ultimate stress 440 Newton per mm square in hot rolled and normalized condition is shown in figure. It is subjected to a completely reversed axial load of 30 kilonewton. Now the notch sensitivity factor Q can be taken as 0.8 and expected reliability is 90%. The size factor is 0.85. The factor of safety is 2. Determine the plate thickness for infinite life. Now how will you proceed with this kind of problem? Hello. So here if you first solve this one, then P is given as plus or minus 30 kilonewton, right? Then SUT is given as 440 Newton per mm square, then reliability is given as 90%, then Q is given as 0.8, and this KB is mentioned as 0.85, right?
Yes.
So first, endurance limit stress can be estimated, right? If it is not mentioned by this estimated will be 0.5 times SUT. So what is this in our case? SUT is 440, so 0.5 SUT will be 220 Newton per mm square. Okay. Hello.
Sir, in every condition we take 0.5 SUT.
If it is not mentioned in our problem, then we can go with this SE dash as 0.5 times SUT. Okay.
Okay.
And Ka in this case is given as 0.67, and when reliability is 0.90, Kc is given as 0.897. These are all tabulated values, right? So you can have this Ka as 0.67 and Kc as 0.897. Now Kt can again be calculated from that figure, right, which we have seen in previous problem. Now I am directly writing Kt as 2.51, right, which can be actually calculated from the D by W ratio as we have seen in that figure 5.2 in previous example. So now once you have all this data with you, then you can calculate Kf actually, right? Kf is given by Q Kt minus 1 plus 1. So you have all the values with you. Q is given as 0.8, Kt is given 2.51. So can you tell me Kf? What is coming Kf?
2.208.
2.51 is sorry, 2.208, right. 2.208 will be your Kf. Now why we have calculated this Kf? Because Kd is 1 upon Kf. So we have Ka, B, C, but we have not that Kd. So in order to calculate Kd, we have first calculated this Kf. Now what is Kf? Sorry, Kd.
KD is 0.453, sir.
0.
KD is 0.453, sir.
Okay. So Kd,
453.
Kd is 0.453. So now can you tell me that corrected SE? Ka, Kb, Kc, Kd into SE dash. So what is this?
591.
50.9 Newton per mm square almost.
Yeah.
Right, so once you calculate this SE, then it is enough or something more needs to be done? By looking at this problem statement, if you remember what I have told
Sir,
you.
for axial load?
Yes,
for axial load?
here axial load is there, so further we will use that SEA is equal to 0.8 SE. So what is it now? 40.72.
40.72 Newton per mm square.
Okay, now you are having this endurance limit. So once you have endurance limit, then you can calculate permissible stress amplitude. Permissible stress amplitude.
20.36, sir.
So permissible, yeah, 20.36, right? This sigma A is
Mhm.
this SEA upon
ACA
factor
by
of safety.
FS.
So that is 20.36 Newton per mm square. So once you have this, then you can calculate the thickness, right? Because this will then be equal to this force P upon W minus T into T. So if you see what is this WD, W is 50, D is 10, correct? And P is anyway given that 30 kilonewton. So 30 into 10 raised to 3 upon 50 minus 10 into T will be equal to this 20.36 Newton per mm.
36.84.
36.84, yes, correct. Go to 36.84 mm. Right, so this is how you are having your this thickness by considering all these factors. Now this next is finite life problem, right? So in order to do this finite life problem, what is first required is you have to have idea. Actually what you need to do is you need to plot this log 10 SUT, right? Then whatever this log 10 SE, at SUT it is generally 3, I guess, and at SE it is this 10 raised to 6. So this way first you need to plot this graph, and then you can see whatever data is given to you, and then you start calculating whether number of cycle is provided or that stress is provided. If number of cycle is provided, then you need to calculate the safe stress for that. If any stress is provided, then you need to calculate the number of cycle, right, to which it is not going to experience any what we can say crack, right? So let us see our problem, how this data is provided in this problem. If you see, a rotating bar made of this steel is subjected to a completely reversed bending stress. The corrected endurance limit is directly given as 350 Newton per mm square. Right, SUT is given as 630. Now calculate the fatigue strength of bar for a life of 90,000 cycles. So here, as you can see, what are the data provided is log 10 SUT and log 10 SE is provided, right? This one, log 10 SUT you can calculate, log 10 SE you can calculate, and you know at which number of cycle is there. Log 10 SUT will be at 3, log 10 SE will be at 6. Then 90,000 cycle you have to make what you can say notation for that 90,000 cycle on this particular graph, and then you need to take it to this particular line, and then you need to take this horizontal in order to calculate that safe stress for 90,000 cycles. So are you getting what I am trying to say? Hello?
Sir, could you repeat it again, sir?
This log 10 will be this log 10 into 90,000 means 9 into 10 raised to 4, right? So this value you will have something log 10 base this 9 into 10 raised to 4 will have something
That's I
value.
got it.
4.95.
4.95.
Okay.
4.95. Okay. Similarly, then log 10 SE will give some value, that is 315, right? Hello? Hello?
Yes, sir. Yes, sir. Yes.
And here you can go up to
So
4 decimal places.
log 10 3
4 decimal places.
log for yes, sir.
For this one, 4.95. Then what is coming?
For logged in 90,000, it's 4.9542.
Okay, 9542.
Yes, sir.
And similarly log 10 SE is what?
2.4983.
Okay. And similarly this log 10 SUT. SUT actually you need to correct with this 0.9 SUT, right? Because this
Huh.
SUT will be at actually that 0 if you remember that high cycle and low cycle. So basically this SUT is that 0.9 SUT and not exact SUT, because you are having this 0.9 to this what we can say, you remember this 0 to 3 you are having this low cycle fatigue, and then this high cycle fatigue, and then this infinite life. Are you getting here this 6?
Huh.
So basically this
2.
you can consider SUT, this you can consider this 0.9 SUT. So log 10.9 SUT is there actually.
2.7536.
2.7536.
Hmm.
Okay. So now once you have this data, you can now calculate it, I guess. What you have to calculate is this value, log 10 SF. Log 10 SF you have
For
to
fatigue
calculate.
strength for 90,000 cycles.
Yes, yes, yes. Can you calculate this with simple interpolation?
Okay, sir.
Or by equal triangle also you can calculate it simply. You can take this
Sir,
true triangle, this equal triangle, this is one, and this may be the other one, right? I guess this way you can proceed.
Sir, how to calculate with equal triangle, sir? By I didn't got it, sir. Could you?
See, what is going to happen is this if you consider this related to 6, you are having this 2.75 see here in this triangle 2.7536 minus this 2.4983. Can you please mute yourself? So 6 minus 3, right, which can be made equal to this 2.7536 minus log 10 SF upon this 6 I guess 1 second, log
सर फैटिग स्ट्रेंथ 381 आ रहा है मेगापास्कल.
1 second. Maybe because of some decimal places you are getting this. It is near to the correct answer, right? So here this
Sir, it is approximately 386.63.
2.753. Sorry?
Actually, it is 386.63.
9,542. Like this way, I guess we can write.
Yes sir, yes.
Correct?
Yes sir.
And from this only you are getting, right? SF is equal to
381 आ रहा है.
386.6.
yeah 386.
63.
It is coming around 386.63 Newton per mm square. Okay, so got it?
Yes sir.
So this is how you are having this finite life and infinite life problem, right? Then next is this cumulative damage. So cumulative damage means whenever you are having that more number of stress amplitude which is having different number of cycles, right? So every time it may not happen that it is having same means it is varying between same maximum and minimum every time. it may happen that more number of cycle with different maximum and minimum is acting on a particular component, right? Like it is mentioned here that plus or minus 350 for 85% of time, then 400 plus or minus 400 for 12% of time, plus or minus 500 for 3% of time. So in that case you have to take into account all the things, right? And at that time this Miner's equation is used, right? This Miner's equation can be helpful in this kind of situation. So this is actually whenever you are having that sigma 1 stress for n1 cycles, sigma 2 for n2 and so on, right? At that time actually whatever this fatigue life is there, so there are n1 such cycles, right? So the damage, right, due to this particular stress can be given as that 1 upon capital N1 into that number of cycle N1, right? N1 is the life for the same force if actually only acting. So similarly for that whatever number you are having here for N2, it may be 1 upon N2 into N2 and so on, whatever number of stresses are there. So basically when you are going to add all this, it can be mentioned as this n1 upon n1 plus n2 upon n2 and so on, right? And it will give you that value 1, right? So basically whenever you are going to use this, then this equation is particularly known as this Miner's equation, right? So that alpha 1, alpha 2, if you are going to consider it as proportion of the total life, right, then see n1 n2 are the life for this particular stress, different stress. So if you consider that n1 is alpha 1, the proportion of that life, right? Similarly for n2 it is having alpha 2 proportion of full life, right? Means n1 is alpha 1 proportion of full life, n2 is alpha 2 proportion of full life. If you consider like this, and if you replace this here in this equation, n1 with this alpha 1 and something like that, then your equation may end up with this alpha 1 upon n1 plus alpha 2 upon n2 and so on up to this it will give you 1, right? So this is how you are having it as alpha 1 to
सर
alpha 1
फिर
is,
N1 ये नहीं होने चाहिए था क्या?
sorry, see n1 नहीं होना चाहिए था means, can you repeat?
नहीं ओके सही है ओके सर.
Right, so this is how you are going to have this full life. 1 second
You're teaching something, some course.
So here as we have seen, this kind of approach can be used to solve this problems where you are having this cumulative damage in fatigue. It means more number of stress cycle are acting for different proportion of time. So by having this idea, now I guess you can try and solve this problem, right? So here work cycle for different things is given, then SUT is given, and then this endurance, corrected endurance limit is directly given, right, for the component as 280 Newton per mm square. So you need to determine the life of component. So can you try this one?
Yes.
So please try this problem. SUT and SE is given, right? SUT is 60 Newton per mm square and this SE is 280 Newton per mm square. So how will you start? First you can plot SN diagram, right, as we have drawn in previous that finite life problem. The very first thing is you need to plot this SN plot.
हाँ सर.
If you try and plot this SN diagram, then first you will have that log 10.9 SUT, right? Then you can have that log 10 SE.
सर प्लीज एक बार क्वेश्चन और दिखा दीजिए.
Yeah. Okay.
ओके सर.
So, can you tell me what is log 10 S.9 SUT and what is log 10 SE?
सर log 10.9 SUT है 2.44716.
2 point, 0.9
2
SUT
point,
is 2.7738.
सर 2.44. अरे नहीं, हाँ 2.773 सॉरी.
हाँ हाँ सर. 2.7738
Okay, okay.
सर.
And this is 2.
और log 10 AC आ रहा है 2.4472.
2.4472. Yeah.
हाँ.
Okay, okay.
और सिग्मा 1 आ रहा है 2.5441.
2.5441 means above this, right?
हाँ.
Look 10s1.
हाँ.
Sigma 1. 2.5441.
41.
Then sigma 2.
Sigma 2.6021.
10 sigma 2 2.6021. Then sigma 3.
Sigma 3 2.6990.
2.6990.
Hmm.
Okay. Then
we have to calculate N1, N2 and N3.
you have to calculate
N1, N2 and N3.
Yeah, yeah. So calculate N1, N2 and N3. हाँ? नहीं. Hello. So first actually you can plot this whatever you have got, right? 2.4472 and this one. Actually whatever that log sigma will come, right? If we consider a particular sigma right here, random, not any particular this sigma 1 or sigma 2 or sigma 3, but if we consider any sigma, for that safe number of cycle is this one. 1 second. Safe number of cycle is this n, right? So you can write an equation for this n. Hello.
Yes sir.
Right. in terms of what we can say this so basically this log 10n you can keep it as it is, right?
सर जो माइनर्स रूल है उसमें log 10 n है या फिर n है केवल?
Sorry,
सर जो माइनर्स रूल है उसमें हम जो यूज कर रहे हैं नंबर ऑफ रिवॉल्यूशन वो लॉग के फॉर्म में यूज करेंगे या फिर केवल
नहीं नहीं
जो वैल्यू है?
वो तो केवल वैल्यूज है ना, वो तो केवल वैल्यूज है, वो तो
Okay, sir.
हियर ओनली वैल्यूज आर देयर, अल्फा 1 and 1 like that. Okay.
ओके सर.
So you need to first have that generalized equation of this log 10n. Or if you don't want to have that generalized, then whatever that sigma 1, sigma 2, sigma 3 you have plotted, you can directly take this from here and then from here. Are you getting? In order to get n1, n2 and n3. Hello? Are you getting?
Yes, sir. Yes, sir.
Like this n1, n2 and n3 you will be able to get from the value of this log 10 sigma 1, log 10 sigma 2 and log 10 sigma 3. Are you getting what I am saying?
Yes, sir. Yes, sir.
So you will have values of n1, n2 and n3. For example, if you go for this n1, then what you will have is let us say this 2.7738 minus
5.1102.
1 second, 6 minus 3 is equal to this 2.7738 minus 2.5441 upon that 6 minus log 10 n1. I guess from this only you have calculated n1, yes or no?
Yes, sir. Yes, sir.
Right? So
Yes, sir. N1 आ रहा है 1,28,000.
128,798.
128,891.
798 and 8,
Okay,
whatever it is near, right?
Yes, sir. Near.
Then n2 and n3, if you go by the similar rule, then n2 and n3 can also be calculated. So what is n2 and n3?
Sir, N2 आ रहा है 37,803,803.
It is here 37,770.
Okay, sir.
And n3 4865. So are you basically getting what we are doing? We are doing it as we are assuming that only sigma 1 is acting, then what may be the number of cycle your component sustain. If sigma 2 is only acting, then what is the number of cycle it may sustain. If sigma 3 is only acting, what may be the number of cycle it can sustain. Are you getting?
Yes, sir. Yes, sir.
So once you have this number of cycles, then that Miner's equation will help you, right? That particular Miner's equation directly you can apply. Hello, right? What is that Miner's equation?
Yes.
Alpha 1 upon n1 plus alpha 2 upon n2 plus alpha 3 upon n3 is equal to
alpha 1 by n.
1 by
Equal
n.
to 1 by n.
1 by n, right? So here actually it is 1 by n, right? Because here n1 n2 when you are going to
Yeah,
replace,
alpha.
it will be alpha 1 and alpha 2, and that is why then alpha 1 by n1 alpha 2 by n2 it will be 1 upon n and not 1. Here it is 1, but in this equation it is 1 by n. Okay.
So as it is mentioned that 85% of time, therefore alpha would be 0.85,
Yeah,
and
yeah,
for
yeah.
400 Newton per mm square,
That point 0.5,
it's 12%.
128,798. Then
Sir, what is the value of n?
that let me first note down this 0.03.4865
Sir, I'm getting 62,723 cycles.
60
Uh,
62.
62,723 cycles.
Yeah, correct. Okay, so all of you are getting the same.
Yeah, sir, उसी range में आ रहा है.
Okay, so once you have this idea, then we can see the last important thing, that is this different criteria which will give us idea about the failure of component, right? So sometimes it may happen that this combination of these forces are acting. So what we are doing is we are plotting this mean stress versus stress amplitude. If you remember, in cyclic stress we have calculated that sigma m and sigma a. It's sigma max plus mean by 2 and max minus mean by 2, right? This is sigma m. Sigma a is this max minus mean by 2. Remember this? While cyclic stress we have seen this. Okay,
Yes, sir.
so by this mean stress and the stress amplitude, we are plotting it against each other, and what we are doing is we are having different criteria. So this Soderberg line and Goodman line is actually only line, as you can see, straight line, this Soderberg line or this Goodman line. While this it is mentioned as Gerber line, but it is actually a parabola, right? As you can see, it is a parabolic curve. So now if we see, this Soderberg line is between this endurance limit and yield strength, while this Goodman line is between that endurance limit and ultimate strength. And this what we can say, this this Gerber line or that parabolic curve is also between this SE and SUT. Actually this Gerber criteria is providing good fit right, for that failure points and all. And Soderberg is the most conservative, right? And if you see, observe clearly, then if your this sigma a is 0, right? If sigma a is 0, then only sigma mean is there, means there is no stress amplitude or alternating stress is not present. In that case, we are only going to consider that SYT and SUT only. It is because converted to static stress only. If your sigma a is 0, then there is no that alternating stress or stress amplitude is there. So your sigma m will be only the stress, right? This mean stress is only acting, and at that time it is considered as static stress, and that is why this yield strength and ultimate strength is being considered, right? Now when this mean stress is 0, we are considering this endurance strength. When this mean stress is 0, we are considering endurance strength, because it is this completely reversed stress in that case. So cyclic stresses are there. So when sigma m is 0, we are considering it as this fatigue stress, or this endurance limit we are considering as failure. Now once we have all this idea about this Gerber line, Soderberg line and Goodman line, what we can do, this Gerber line and this Goodman line are from simple that line x upon a plus y upon b is equal to 1, and if you are considering that factor of safety, then it is x upon a plus y upon b is equal to 1 upon factor of safety. This way both can be represented, while this parabolic will be represented as that equation of that parabola, right? But one important thing here to notice is if you plot this line, yield line, right, yield point on both the axes, stress amplitude as well as mean stress, if you plot this line, then if your point is outside this line, right, then also this particular Goodman line is giving you a safe point here also. But if your component is crossing this SYT, then sometimes it is not possible to perform the intended task because plastic deformation may start beyond this point, and which is not desirable. So that is why there is a modified Goodman line will be there, right? So actually this way, if you see more clearly, if I expand, then here this SYT, this yield line is there, right? And if you draw your that which line we can say, this Goodman line, then it is going from this SE to this here also. It is not clear, let me draw it more clearly, 1 second. So if we draw that again here, see here, this is, let us say, SYT, and it will have almost angle of 45 degrees because from both axes we are having this SYT. It is called yield line, right? Now Goodman line is between this SE and SUT, so it will be going to like this. Now the point is, if any component is crossing this yield line and it is lying in this region, then according to Goodman line, this is Goodman line, it is in the safe region, right, according to Goodman line, because it is below this Goodman line, but it has already crossed this yield line, so it means plastic deformation has started, so it cannot be considered as safe point. So there is a modified Goodman line. Modified Goodman line is there, which is going to be from here to here, it is same, but it will not go into this region. It will then go by this way. This is known as this modified Goodman line. Are you getting what I am trying to say? Hello?
Yes, sir.
Yes, sir.
So this is how you can have your this different lines, right, and this parabola. So now if you understood this, then we can start solving some problem. Is it okay? Hello? Hello?
Yes, sir. Yes. Yes, sir.
Okay. So here, this one. So I guess this is straightforward question, right? This can anyone tell what is this north sensitivity factor? Hello, we have just now discussed, right?
Yes, sir. A.
A, sir. A.
Kf minus 1 upon Kt minus 1.
Hmm.
This is also simple, right? When the for steel
10 to
when
the power 6.
it has become a simple.
10 to the power 6 cycle.
Yes, okay,
Uh-huh.
good. Then the next, for this one, for cylindrical object subjected to alternating stress of 100 megapascal and fatigue strength to sustain 1000 cycle is 490 megapascal. If the corrected endurance strength is 70 megapascal, estimated afterlife. Can you calculate this?
Yes, sir.
Please calculate. Here you are given for 1000 cycle, means this value is directly 0.9 SUT only. Are you getting? Yes or no? Because at
Yes, sir.
3 only we are having this, right?
Huh.
And for 6 we will have this SE, that is 70. That will be for 6. So this way you will have your graph, I guess. Yes or no?
So C, sir.
C, huh?
Huh.
All of you are getting this?
Sir, just solve.
Mm-hmm. So 100 megapascal they are asking, right? So 100 megapascal will be log 10 100, huh? Okay. For that you have to calculate this n. So basically, what is log 10 490? What is log 10 490?
Sir, 2.6902.
Okay, this is 2.6902 and log 1070. 1.8451. Log 10 100 will be 2. So from this 2.6902 minus 1.8451 divided by 6 minus 3 is equal to this 2.6902 minus this 2 minus 2, right? 1 second. Minus 2 upon this 6 minus log 10. This will give you answer, I guess. Yes or no?
Yeah, yes, sir.
So this n will be equal to what?
3.
Huh? C, right? 281914.
Huh. Huh, sir.
Okay. The next is this a thin spherical pressure vessel of 200 mm diameter and 1 mm thickness is subjected to an internal pressure varying from 4 to 8 megapascal. Assume that the yield, ultimate and endurance limit of the material are 600, 800 and 400 megapascal. The factor of safety as per this Goodman's relation we need to calculate, right? So can you try this one? Hello? Hello?
Yes, sir. Yes. Yes, sir.
So here actually you need to calculate this sigma 1 and sigma 2, right? From this P max and P mean, which is given as 4 and 8 megapascal, into R by 2T, and that is the equation PR by 2T. Okay. R will be 100, T is 1, P max and P min is given as 8 and 4. So for both actually sigma 1 max actually both principal stress sigma 1 max and sigma 1 mean, similarly sigma 2 max and sigma 2 mean you need to calculate with this relation. So which will be that 400 and 200, I guess. Yes or no? 200 megapascal
Yes, sir.
and 400
Start.
megapascal. So here also
Then
200
we have to
megapascal.
calculate mean stress and variable stress.
No, then you have to calculate actually this what we can say equivalent stress you have to calculate, right, first by considering any of the failure criteria. If you consider that maximum distortion energy theory.
Sir, if we calculate it by mean stress and variable stress, then what problem would it be?
Yeah. After actually calculating that mean stress and that variable stress, you have to go for that safe stress as per those failure theory. First, you have to calculate that sigma 1 mean and sigma 1 alternating, then sigma 2 mean and sigma 2 alternating. So that is 400 plus 200 by 2, 300. Then 400 minus 200 by 2, that is 100. Similarly here also, right? You are getting this, right? Because sigma m is equal to sigma max plus mean by 2.
Sir, factor of safety
And
means the
sigma,
Goodman line is shifting toward origin with the same slope.
sorry.
Sir, factor of safety means Goodman line is shifting toward origin with the same slope.
Yes.
Okay.
So once you have calculated this sigma 1m and this sigma 2m, then you can calculate equivalent stresses, that mean equivalent and that alternating equivalent, by using that any of the failure theory. Here we are considering that
1.6.
distortion energy. So actually this both you will get same sigma, because here it is sigma 1m square sigma 2m square minus sigma 1m sigma 2m. As you can see, sigma 1 is equal to sigma 2m. It will be any of the sigma 1m or sigma 2m, which is same, and same will happen to this AE also. Yes or no? Hello? Can you?
Yes, sir.
Yes, sir.
And
Yes, sir.
what is this Goodman line? That is this
Sir, 1.6.
alternating upon this SE and this mean upon SUT is equal to this 1 upon n, because in your Goodman line you are having this kind of what you can say, here SE and here SUT. This is sigma m and this is sigma a. So x upon a plus y upon b is equal to this 1 upon factor of safety. So x is sigma m, and on that intercept is SUT. On y it is sigma a and intercept is SE, and then this way if you will use 100 upon, what is SE? What is SE?
400, sir.
And SUT?
800, sir.
800.
Okay, so this will give you n is equal to 1.6, correct?
Yes, sir.
Okay. So next, let us say this one. A forged steel link with uniform diameter 30 mm at the center is subject to an axial force that varies from 40 kN in compression to 160 kN in tension. Tensile yield and corrected endurance strength of the steel material are 600 megapascal, 420 megapascal and 240 megapascal respectively. The factor of safety against fatigue endurance as per Soderberg equation. It can be calculated, right? It is easy again.
Yes, sir.
Calculate it. So for this, I guess what you need to first do is first you need to calculate that sigma max and sigma mean from this force, right? Sigma max and sigma mean you need to calculate first from the given force. The diameter is 30 mm, so maximum force is 160 kilonewton in tension and minus 40 in this compression, so it will be 10 raised to 3, right? Divided by pi by 4 d square. D is 30 mm.
That is maximum is coming 2 to 6.47.
Okay. And then
सर मेरा मीन और एक्सियल वो आ गया
sorry,
एम्पलीट्यूड
हाँ,
सर मीन और एम्पलीट्यूड निकल गया है
ओके मिनिमम आ रहा है -56.62
और सर सिग्मा मीन आ रहा है
हाँ,
और
सिग्मा मीन और सिग्मा ए बता दीजिए. सिग्मा मीन क्या आ रहा है?
गलती हो गई सर सॉरी
Sigma mean 84.925.
Okay. Then sigma A. What is sigma A?
141.545.
Okay. So now Soderberg equation, you know, right? Soderberg equation.
हाँ सर.
So Soderberg line, you know. 1 second. Please mute yourself.
Sorry sir, sorry.
So Soderberg equation, you know, this is sigma A, this is sigma M. In case of Soderberg, it is from SE to here SYT. So it will be sigma M by SYT plus sigma A by SE is equal to 1 upon N. What is sigma M and sigma A? You know, that is 141.54, right? Sigma A is 141.54 only, right? Yeah, and this is 84.925. SYT is what? 240. This is 420. So what is N? Vector of safety? What is,
Sir 1.26.
so N is coming 1.26. So this is how you can calculate this, right? 1.26 is given here. Okay, is it okay?
सर
Okay, so let us go to the next one. Here a bar is subjected to fluctuating tensile load of 20 kilonewton to 100 kilonewton. Then the material has yield strength of 240 megapascal. Endurance limit in reverse bending is 160 megapascal. According to Soderberg principle, the area of cross section of the bar for a factor of safety 2 is. You can do this also, right? Hello.
यस सर
Here first you can calculate this mean and that amplitude in terms of force only, then you can put it as that force mean upon area and force amplitude upon area. Are you getting what I'm trying to say?
Yes, sir. Yes, sir.
So you can calculate that mean force and amplitude force at P max plus mean by 2, that is 60, right? And 100 minus 20 by 2, that is 40 kilonewton. Yes or no? Hello?
Yes, sir. Yes, sir.
So sigma m and sigma a can be then written by this, and
Sir,
then
cross section है क्या?
cross sectional area is not there, so you are calculating first force and then directly dividing it by area, and then you can apply this Soderberg equation, sigma m upon s by t plus sigma a upon se is equal to 1 upon factor of safety. Factor of safety is given here, so only unknown is area.
Sir, 1000 आ रहा है क्या?
Yes, correct. So sigma m is this 60 into 10 raised to 3 upon s by t is 240 and se is 160. Se is 160, right? Right, when you solve this, you will get A is equal to 1000, correct? Mm square.
Yes, sir.
So from this so many questions are asked actually from this area, right? And it is easy, right? Are you getting now what we are solving is?
Yes, sir. Yes, sir.
So next is this: in structure subjected to fatigue loading, the minimum and maximum stresses develop at 200 and 400 mm. Then the stress amplitude. It is very simple, right?
100.
Huh?
100.
Let us see. What others are getting? It is actually straight away maximum minus minimum by 2. Yes or no? So the next question is: a rotating steel shaft is supported at the ends. It is subjected to a point load at the center. The maximum bending stress developed is 100 megapascal. If the yield ultimate and corrected endurance limit is 300, 500 and 200 megapascals respectively, then the factor of safety for the shaft is. How will you solve this one? Can you try? Hello?
Yes, sir. Try कर लें.
Please try this.
तो सर FS2 आ रहा है.
Yes, correct. Because here see, only that magnitude is given, means you are assuming that sigma max and sigma mean both. In bending you are having that plus and minus, right? So plus 100 megapascal and minus 100 megapascal. If you consider this, then sigma mean will be 0, sigma A will be 100. And when you go for that equation, let us say Soderberg criteria, it is most conservative. So sigma m by sigma y plus sigma a by sigma e. So nothing is given, then you are going for this most conservative design. So that component is not going to fail. So sigma m is 0, then sigma a is 100. Endurance is given as 200, corrected endurance, then 1 upon n. So it means n is equal to 2. Okay. Hello.
Yes, sir.
Next is, which one of the following is most conservative? Just now I have told you, right?
A, sir. Sortable.
Okay. So now next is, yeah, this is something different. For given fluctuating this fatigue load, values of stress amplitude and stress ratio, can you calculate this?
Sir, 100 has stress.
Sorry,
100 is the amplitude.
100 is,
Stress amplitude.
okay, correct. 100 is stress amplitude, that is the correct, because 250 minus 50 by 2, right? It is visible from the figure. Okay. Now what is stress ratio? Stress ratio is sigma minimum by
Sigma maximum.
maximum. So what is this?
C data, sir, 0.2.
0.2, huh? Okay.
Yes.
So C will be the answer. Okay. Now next is, here a machine element has an ultimate strength of 600 Newton per mm square and endurance limit of 250 Newton per mm square. The fatigue curve for the element on a log plot is shown below. Now if the element is to be designed for a finite life of 10,000 cycles, the maximum amplitude of a completely reversed operating stress is in Newton per mm square. You have to calculate. So can you try this one? Hello. Are you trying?
Yes, sir.
Please try. I guess it is same what we have solved. You will be able to do this, I guess.
Sir, 386.19.
Correct. 386.195 is the correct answer. Now how you got it is clear, right? Here the point will be 3 and this log
Yes.
10 480,
Huh.
right? Here the point is 6 and this log 10 250,
Log
right?
10 to 50.
Right, log 10
Hmm.
250, right? We have solved many of this kind of questions, right? And what else is given? 10,000 cycles for a finite life of 10,000 cycles. So that is 10 raised to 4, right?
Yes.
So that is what you need to calculate is this stress you need to calculate, right? This
So PB to S.
10 SF you need to calculate for 10,000 cycle. So if you again go by whatever we have calculated, you will get this. I am not showing calculation. I guess you will be able to do this, right?
Sir, it's same like
Okay,
similar
okay.
like with the
Yeah. So next is a machine component made of ductile material is subjected to a variable loading with sigma minimum is -50, sigma maximum is 50, corrected endurance limit is 100 megapascal, yield strength is 300, the factor of safety. Can you calculate this? क्या काम था आपको? Okay. Yes, so are you trying?
yes sir.
Okay. Here again that sigma m will be 0 and sigma a will be that sigma max, right? So that 50 is there, right?
Sir, 2 are
Again it will be 2, right? So similarly what we have done previously, again it will be coming 2 only. For that Soderbergh you can try and you will get
So
this.
if, nothing's given, should we consider soda book, sir?
Yeah.
Okay.
Now next is this fatigue life of a material for a fully reversed loading condition is estimated from this sigma is equal to 1100 and raised to minus 0.15, where sigma is stress amplitude in megapascal and n is the failure life of in cycles. The maximum allowable stress amplitude in megapascal for a life of 1 into 10 raised to 5 cycles under the same loading condition is. Okay, so can you try this?
okay.
Fully reversed load means again it will be same, right? So the sigma a sigma mean will be 0, then sigma a will be sigma max, and that sigma max will be equal to this 1100 n raised to minus 0.15, and you are asked for 10 raised to 5 cycles. So if you put n is equal to 10 raised to 5, then you will get that sigma max. Are you getting? It is simple, I guess, right? Hello. See here,
Yes sir, yes sir.
fully reversed load is given means sigma mean will be again 0 and sigma a is equal to sigma max only, right? And sigma a is
sir.
given by this, yes or no?
195.61 megapascal.
Okay, yes. So then sigma max is equal to 1100 into this 10 raised to 5 raised to minus 0.15, so which will give you 195.61.
Sir.
Okay, thank you. Now next, try the next one. A bar is subjected to a combination of a safety load of 60 kilonewton and a load fluctuating between minus 10 kilonewton and 90 kilonewton. The corrected endurance limit is 150 megapascal, yield strength is 480, ultimate strength is 600. The bar cross section is square with side A. If the factor of safety is 2, find the value. I guess this is same which we have find that area, right? Are you getting? Hello.
Yes, sir. We have to find the area, then we will get the length.
Right.
Sir.
So I guess
So that is
you can do.
31.62.
Yeah. 31.62 will be the answer. I guess you can do this, right?
Sir. So this topic is bit easy in comparison to others, but we
Yeah.
have to keep that in mind when we should apply the Soderbergh equation or
Yes,
like this thing.
yes. So next is this during high cycle fatigue test, a metallic specimen is subjected to cyclic loading with mean stress of 140 megapascal, minimum stress of minus
Sir,
70 megapascal. The R ratio.
sir,
Yeah,
how many questions are left, sir?
I guess let me check. 3 question after that. It will not take that time. 5 minutes, I guess. Okay.
Okay, sir.
Yeah. So this you can try, I guess. Here sigma mean is given as 140, right? Mean stress, and minimum stress is given as minus 70, right? So sigma mean is 140, then sigma max plus sigma mean, right? Where minus is given as sigma mean. So you can calculate sigma max first. What is sigma max? (350 megapascal), right? Hello. Hello.
Yes, sir. Calculating, sir. Calculating.
Okay, and then that R ratio is minimum stress to maximum stress. That is minimum to maximum. That is this minus 70 to 350. That is minus 0.2. Okay, it is simple.
Sir. Minus 0.2.
Okay. Then next is endurance limit of a beam subjected to pure bending decreases with. Can you see this one? Try this one.
Sir, will it be increase in the surface roughness and decrease in the size of beam?
Sorry.
No.
This one, right? See, increases in the surface roughness and
Surface
increases
roughness
in the
and
size of beam, right?
size of beam.
Right.
Sir.
Okay. If surface roughness is increases, then this endurance limit will decrease, and size increases, then also it will decrease. The next is the machine is subjected to this fluctuating stress, then the endurance limit is this, factor of safety used is this 3.5, then the sigma naught is. You can calculate this.
Sir.
Try and calculate. See, maximum and minimum will be at cos maximum and minimum, right? So maximum will be sigma naught, minimum will be minus sigma naught, right? So this way sigma mean will be 0, sigma a will be sigma max or sigma naught, you can say, right? That sigma e is given, factor of safety is also given, right?
100.
Yeah. So sigma naught can be calculated because factor of safety is given and sigma e is given. Sigma e is also given.
The sigma is also given.
So that sigma naught can be calculated from any of that conservative, that Soderbergh line or something. So it is 100, right? Okay, and then last one is this. Last one is this. Again, it can be calculated easily, right? So I guess we can.
Sir,
Yeah.
would it seems like we did it previously.
Sorry,
Actually, it seems like we did it previously. Earlier we
I
did that.
I don't know. Maybe we will check. You can check it, right? So this is again same question, right? That we have solved this kind of question, I guess. So you can do it by yourself. This also, right?
Yes.
Okay. So is there any other question for today's session?
Sir, actually, as you are telling that when we should apply this equation, like Soderberg equation or like that,
Mm-hmm.
but how to remind that we should apply this Soderberg equation or Goodman's line
See, until and
during
unless
that
they
time?
have specifically asked, then you can
Huh.
directly apply this Soderberg equation because it is conservative equation, right? So your design will be
Okay, sir.
safe. Huh.
Sir, for this problem, the cycle would be 1,63,842.
Yeah, yeah, 840 or whatever, near to that.
Hmm.
Correct, correct.
Uh-huh.
Okay then.